Bismillahirrahmanirrahim. Today's topic is multi-point constraints, also called MPC. Uh, this is an extension of the penalty approach that you have already studied in the last lectures. There, the penalty method that we studied was for specified boundary conditions. I'll come to this word specified. In this case, the boundary conditions take this form. That is, the values of u1 and u2, any two degrees of freedom, they are not specified. You don't know them. u1 and u2 are not specified. Their relationship is, only the relationship is specified. That is, a certain number multiplied by u1 plus a certain number multiplied by u2 is another number. Now contrast this with the specified boundary conditions that you have been dealing with in the past. Contrast with, for example, u1 is equal to 2 millimeters. This is a specified boundary condition. You know the number. u5 is equal to 5 millimeter. u6 is equal to z. This is a very common boundary condition. Zero boundary condition. These you have been encountering quite frequently, but this is the first time you are encountering something like this. Namely, you don't know u1, the value of u1 or the value of u2, but there's a relationship that is known to you. So we are going to approach this method by the same route that we approach the penalty method for specified boundary conditions, and you'll see many familiarities. You'll be seeing similar things that we go through here. There we started with the potential energy, total potential energy expression, and this is so familiar to you that there's no need to explain this now. We've done it so many times already. This is the total potential energy expression for any system. Now, if a boundary condition like this is to be applied, then you need to add another term, and those who are familiar with the penalty approach, they know that what this number c is. I'm going to repeat it again here, but you have to add this term here. I'll explain this term. Now, a very large number is applied to this expression, and this whole expression this term gets added to the potential energy expression. This is actually the strain energy of the system. This is the strain energy of part of the strain energy of the system. It gets added to the potential energy expression because of the multi-point boundary conditions. Now, you know that for any system to be in equilibrium, and we are dealing with the steady state systems, this potential energy of the system gets minimized. So when will this whole system, this whole expression becomes minimized? Considering that c is a very large number, and we are going to consider this number in concrete terms when we come to that. But if c is a very large number, when will this expression be minimized, the value of this? So let's write it down here. c is a very large number, so this total potential energy takes a minimum value only when does it get minimized? This is very large, this must be very small. When this expression becomes very small, then this takes minimum value, and hence this whole expression takes minimum value. When beta 1 u1 plus beta 2 u2 minus beta naught is very small. In other words, not exactly 0, but it will be very close to 0. That is what being minimum means. And if we rewrite it, this means if this is minimum, then this means this. And what is this if not the expression that we started with? This is what we sought to apply on the system. So by choosing this term to be minimized, this in other words means that this expression gets applied to the system. That is what we required in the first place. So this is how we approach this problem. Now, those of you who have studied the penalty approach for single specified constraints, they would recall a slightly different expression here, but the thinking is exactly the same. So there's no difficulty here. Once we get this expression, the next step is obviously to minimize the potential energy, because for equilibrium the potential energy gets minimized, and mathematically you can express this process as this. We minimize the potential energy by differentiating this expression with respect to the vector of all the degrees of freedom from un to u1 to un, and equate the system to the system of equations to 0. Now, if we only take the first term, this term, and the third term, and for the moment neglect this term, then the minimization of this and this alone is very familiar to you. So there's no point spending much time on that one here. K11. This is how we achieve our FEM solutions, always by minimization. And this is the very familiar FEM equation format that you have seen so many times: K11, K22, K23, K2n, similarly K31, K32, K33, K3n, Kn1, Kn2, Kn3, Knn. Whatever the size of the system may be, in the end you get this format all the way up to un. Similarly for the force vector, F1, F2, F3, Fn. And let me put the parenthesis not here but here, and this will become clear soon. Now, what about the term that we ignored? In this system, this term is very much a part of the system. In fact, this is how we apply the boundary conditions that were given to us. So we have to minimize this also, and then put it in the relevant places. And if we do that, we can write that process, because this is minus that term. For that term alone, let's call it the penalty term. So this expression now only contains the penalty term, because the rest we have already dealt with here. So this takes the form, not the whole u vector, only the relevant terms, because your boundary conditions in this case, for this example, they are applied on u1 and u2 alone. So there's no point differentiating this term with respect to any other degree of freedom from u3 to un, because you are going to get a 0. So you're not going to waste time there. And the expression itself is, this is the expression that we added to the potential energy expression. Now this we have to differentiate. So if we differentiate with respect to u1 first, so we get 2 gets cancelled, b1 u1 plus beta 2 u2 minus beta naught differentiating with respect to u1, so we also get a beta 1 here. Upon rewriting, c beta 1 square u1 plus c beta 1 beta 2 u2 minus c beta naught beta 1. Now it goes without saying that this part, this term, this gets added to the first row, because the first row is what you get when you differentiate that expression, this expression with respect to u1. You get this first. So for u2, the next one, when you differentiate this one, the expression we get should be added to u2, this line, second row 2, because the second, this is the equation k21 u1 plus k22 u2 plus k2. This is the expression, this is the equation that we get when we differentiate this whole expression with respect to u2. So if we do that now, again get a very similar expression, except obviously here we have now beta 2 here, and upon rewriting, c beta 1 beta 2 u1 plus c beta 2 square u2 minus c beta naught beta 2, and this thing gets added to the second row. Now where in the first and the second row? That's very obvious. This c beta 1 gets multiplied with u1, so this gets added, and you would have noticed the similarity with the penalty method. This is the penalty method, only you are dealing with multi-point constraints here. Now this u2, this term gets added to, this gets multiplied to u2, so this can only be added here. This term c beta naught beta 1, there's no u1 or u2 or u3 here, so on the left hand side it cannot be accommodated. It's a constant, goes to the right hand side. Similarly, second row, this multiplies u1, so it's very obvious. Here this gets multiplied u2, so and this is a constant term. I beg your pardon, this is beta 2, not beta naught. This is all you need to do to apply multi-point constraints on a system is this. You get the value, you write that equation, whatever, you'll have some numbers for beta 1 and beta 2 given, this will also be given, and all you need to do is take those numbers, select a c, and c, like always, will depend on the K matrix itself, the highest number of the K matrix multiplied by some very big number. So you add those things in the relevant parts of this matrix, and that is all you do to apply the boundary condition. The boundary condition has been applied here, so in a certain sense our work is done. But and this is how simple it is. That's all you need to do. When you'll solve this sort of a system and you get the values of u1 to un, then you will realize at the end that whatever the relationship between u1 and u2 was, your relationship, that relationship will have been applied by virtue of your changing the equations into this format. Now, in a certain sense, our job is done. But since we sometimes also have to calculate the reaction forces, usually we don't. Very often, we don't need that. But sometimes, in rare cases, we may need to calculate the reaction forces as well. So for that, we need to do some more work in case that becomes necessary. For reaction forces, let's write the first two equations separately. Let's open these matrices. K11 U1 plus C beta 1 square U1 plus K12 U2 plus C beta 1 beta 2 U2 plus k13 u3 all the way till k1 and un is equal to f1 plus c beta naught beta 1. This is the first equation. The second equation, because these are the only two equations where we need to find the reaction forces. These are the u1 and u2 are the boundary conditions actually applied here. So you need to find the reaction forces for these. Second equation, k21 u1 plus c beta 1 beta 2 u2 u1. Still, this is also multiplied with u1 plus k22 u2 plus c beta 2 square u2. Again, both of these get multiplied to u2 plus k23 u3 plus all the way to k2n un is equal to f2 plus c beta naught beta 2. The rest, they are unchanged. No boundary condition has been applied. In fact, in those cases where you are not applying boundary conditions, you will apply the forces. So that's another topic. We are not going into that one here. The terms in these equations that are new are these, this one, this one, this one, similarly this one, and this one. By a simple rearrangement of these equations, and recall that we are only doing this for reaction forces. Boundary conditions have already been applied. If we rearrange this system so that these terms, new terms, they go to that side, and the original terms including f1 and f2, they are on the left hand side. So we bring f1 f2 here and these new terms to the right hand side. Then this is what we get: k11 u1 plus k12 u2 plus k13 u3. This is the original FEM equation, the first row of the equation, minus f1. On the right hand side you get, with the sign changed, minus c beta 1 square u1 minus c beta 1 beta 2 u2 plus c. This one was originally here, so no sign changed. Now this one is, if you recall, this is the original equation of FM. And the right hand side, this then becomes R1, the reaction force with boundary conditions applied. Without boundary conditions applied, you have this is equal to 0. With boundary conditions applied, because the original equation, recall, k11 u1 plus k12 u2 plus and so on is equal to f1. This is equal, this part is equal to f1. So if you bring this f1 here, then this originally without boundary condition applied, the right hand side should be 0. If you bring f1 from the right hand side, let me be clear here, this often is a point of confusion here. If in this equation, the first equation, there is no these values, these things are not there, only focus on the quantities in black, then left hand side is equal to right hand side. And if you take f1 from the right hand side to the left hand side, you'll get 0. On the right hand side 0. This is before the boundary conditions are applied. If you apply the boundary conditions, then we see that the right hand side, even if you bring f1 from the right hand side to the left hand side, there is something on the right hand side. It is not 0 and it should not be 0, because now you are applying the boundary conditions. So whatever you get on the right hand side, that is the reaction force, R1. Similar procedure, k21 u1, again rewriting of the equation, second equation of our interest. Minus f2 now. This will be similar in shape but slight b1 beta 1 beta 2 here, beta 1 beta 2 u1 minus c beta 2 square u2 plus c beta naught beta 2. Now this one again by the same process, this is nothing but R2 or the reaction force with boundary conditions applied. Reaction force 2, because this part is the original equation. Let me again do it more explicitly here. K11, K12, K13, K1n. This one gets multiplied with U1, U2, U3, Un is equal to F1. This is the first equation is this. K11 U1 plus K12 U2. Now, if you take F1 from the right hand side to the left hand side, then because this is equal to this, then these quantities are the same, right and left hand side. So if you take F1 from right to left, then this K11 U1 plus K12 U2 plus K13 U3 K1n Un minus F1 is equal to 0. Then this quantity is 0. But this is before the application of boundary conditions, as it should be. But if you apply the boundary conditions, as we have seen, when we apply the boundary conditions, we have to have a certain term added here. And this term, when you differentiate it and then you modify your expressions accordingly, then you see that some new terms in blue come as a result. So when this comes, you rewrite this equation again, F1 to the left hand side. You see now that even if you bring F1 to the left hand side, it's not 0, because you have still a quantity there. So that quantity is the reaction force, and that reaction force is precisely there because it is forcing some sort of a displacement at U1. Obviously it's also doing at U2, but some sort of constraint is there, and some constraint is always there when there is a force, that some force causes that constraint, and that is the reaction force. So in other words, if now our job is done, R1 then takes the form minus C beta 1 square U1 minus C beta 1 beta 2 U2 plus C beta naught beta 1, or written in a slightly different form, minus C beta 1 U1 plus beta 2 U2 minus beta naught. This is the value of R1. Should you want to calculate it, normally you won't be required to do that, because once we have the displacements, we go on to strains and then stresses, so reaction forces are hardly ever computed. But if you want to, you can do it. Then R2 again minus C beta 1 beta 2 U1 minus C beta naught square U2 plus C beta naught beta 2, again written in a slightly different form, beta 1 U1 plus beta 2 U2 minus beta naught. This is how you calculate the reaction force 2. Now, why we wrote it in this form? First of all, we have inside the bracket we have the same beta 1 U1 plus beta 2 U2 minus beta naught, and which is nothing but the original melting point constraint. Easy to remember. And the only difference being outside the bracket you have here minus C beta 1, here you have minus C beta 2. That's all. So this is how you apply the boundary conditions, and this is how you calculate the reaction forces if needed, and this is rarely needed. Now we reinforce our learning, whatever we did, by applying it to a concrete problem. A naval brass tube. Naval brass is just kind of a brass, so nothing to worry about. A naval brass tube is fitted inside a steel nut bolt arrangement. This nut and bolt and nut, these are of steel, and you have a tube inside. After the nut has been fitted snugly, you have just rotated the nut so that it touches the tube. You're not applying any forces here. That is snug fit. It is tightened 1/4 of a turn. Once it is touching the tube, now you apply 1/4 of a turn. Now you are basically squeezing the tube. Given that the bolt is single threaded with a 1.6 millimeter pitch, determine the stress in the bolt and the tube. So this is the question. It says single threaded. Single threaded is simply nothing but you have just number of starts is 1. Number of starts n is equal to 1. That means you have this relationship between the pitch and the lead. This is the lead. And if for single thread you have n is equal to 1, so your pitch and the lead are the same. So what you need to do here is just focus on the pitch, because lead is equal to the pitch. And what is the pitch? Pitch is given as 1.6, so the lead is also 1.6. And what is lead but linear advance of the nut in one revolution. You rotate the nut once, it advances 1.6 millimeter. That's all. But here in this case, we only rotated the nut 1/4 of a turn. So one revolution is 360 degrees. So 1/4, your only actual rotation is equal to 90 degrees. So that is 1/4 of a turn, right? 1/4 of a turn you have actually rotated the nut, and that means 1/4 of the pitch. Your nut has advanced by 1/6/4 is equal to 0.4 millimeters. Now this is an interesting thing. You rotate the nut, it ought to advance. If there was no tube here, brass tube, then your nut would have advanced exactly 0.4 millimeter. But now what happens is, this tightening of the nut, it elongates this steel bolt, and at the same time it compresses the naval tube and naval brass tube. So we don't know yet how much the steel bar extends and how much the naval tube shrinks as a result of this application or this turning of the nut. But we know one thing for sure, and that is the combination of extension of the bolt and contraction in the tube, that is equal to 0.4, because 0.4 is the amount of advance by the nut. If I draw it here graphically, let me do it to make the understanding even simpler, even if you don't understand yet. Just one more approach to show what is actually happening here. Let's call this one your bolt. This is element 1, this is element 2. We are going to FEM, so we are going to model it with two elements, 1 and 2. At this 2, make no mistake, this 2 contains this tube hole. This is also part of 2. Okay. Now, when we talk about nodes, this is node 1. Let's call this node 2. And this point is common, so this is node 3. This is steel bolt. This is brass tube. Now this is before the rotating of the nut, and this is coordinate axis is very important. This is the positive x coordinate. When you rotate it, what happens? The tube shrinks, the bolt extends. So this is our reference line. This remains the same. This is the original datum. Now 2 dash is the new point of the new location of the end of the end. By the end I mean the point where the bolt enters the nut. This is the new position. But as far as the brass is concerned, this is the new location. It has contracted. Now what is 0.4 but? the combination of the two. That is what 0.4 means. So it's not that kind of a problem in which you have this one node and you have this two node which is the same, and then whatever happens to 2 also happens to 3, so you have the same boundary condition. No, this what 2 and 3 are linked in a certain sense, but they are not. First of all, we don't know the value of 2, we don't know the value of 3, but we know that displacement in 2 and the displacement in 3, they add up to 0.4. We don't know what u2 is, we don't know what u3 is, but we know their combination. And the combination, if I write it here, is nothing but u2, this is u2, and this is u3 minus u. I'll write minus because u3 is in the opposite direction to the positive x-axis. So if u2 is positive, then u3 is negative. u2 minus u3 is equal to 0.4. Now, what was our multi-point format? b2 u2. I'm just changing these. We did b1 beta 1 u1 plus beta 2 u2, but here it's more suitable to use because we have u2 and u3, but doesn't matter. Beta 2 u2 plus beta 3 u3 is equal to 0.4, which means that beta 2 for our case is 1, beta 3 for our case is minus 1 for this kind of loading, and beta naught is 0.4. That is all. So this is how multi-point constraint questions appear. Now this is one of the multi-point constraint problem. This you cannot do with simple application of specified boundary condition. There is no specified boundary condition. Yes, there is u1. This node 1. This is common to both node 1. This is 0. So we should also, in the interest of accuracy, you should write that u1 is equal to 0. This is specified, yes. But if you only specify this one, then you will not be able to get the right solution where this relationship is also maintained. So you also want to apply this one. So this is basically multi-point constraint. We have to apply both of these. Obviously, the first part is not to apply boundary conditions, but to first make the elemental and then the assembly equations. So this, you have 1 and 2, and if we make a connectivity table, this has nothing to do with boundary conditions. Elements, nodes, I, J. This part of the problem has nothing to do with boundary conditions. This is just the standard, what we do always. Element 1 has nodes 1 and 2. 1 is common to both. Element 2 has nodes 1 and 3. This is your connectivity table. Now let's start with elemental equations. K1, first element. Elemental equations obviously take this form, AE over L. This is 1D system, 1 minus 1 minus 1 1. This is the value of K. Very familiar. So just put in the values, and this basically you have all the values here. For element 1 you have the diameter is 10 millimeter. Material is steel. E is equal to 200 steel, and the length here is 100 millimeters. We need the length. Without length we cannot do this problem. Okay, let's take this as 100 millimeter. So you have all the information now. AE over L, diameter 10 millimeter is there, so nothing difficult about it. A pi by 4 into 10 square. E 200 into 10 raised to power 3. This is our Young modulus converted to megapascals. Length 100 millimeter. 1 minus 1 minus 1 1, and this turns out to be 5000 pi. I'm deliberately I'm writing it in this form. I don't want to lose information here. As you'll see in this problem and in all penalty method problems, we use a very high penalty number C, and that because that is very high and it gets applied to many diagonal elements and some off diagonal elements also, as you'll see. So the system becomes very sensitive to any errors. So we would like to use accuracy as much as possible. So if you're doing it with your calculator, try not to write it in the form of decimal points, because then you'll lose information in every step, and in the end you might have some errors. So we are trying to avoid that. If you're using your computer, some sort of algorithm or Excel, then the problem becomes easier, because then you can use double precision arithmetic. So, and that is advisable. So here I'm just doing it by hand, so I'll keep this pi here. Okay. It's always good practice to lose as little information as possible, especially in these problems. Now this, the other one, the brass. For brass you have outer diameter 18, inner diameter 12, and the brass, naval brass, Young modulus E is 100 GPa. The length is the same, so you just plug in the values. And this turns out to be 45,000 pi. This is 50,000, I'm sorry. This is 50,000 pi, this is 45,000 pi. 1 minus 1 minus 1 1. Now, from your connectivity table, this is 1 2 1 2. This is 1 3 1 3. So when you assemble to make this system matrix, you have 1 2 3 1 2 3. Put in the values by using the connectivity. The first element 1 and 2, the second element 1 and 3. So it's a simple matter of putting these 1 2 1 2 here and 1 3 1 3 1 3. So again, very familiar, nothing to do with boundary conditions yet. 50,000 pi minus 50,000 pi minus 50,000 pi 50,000 pi. This is element 1 superimposed. Now element 2, the first 1 1 again, plus 45,000 pi, but this comes in the place of 3 1 or 1 3, minus 45,000 pi minus 45,000 pi 45,000 pi 0 0. Here you have u1 u2 u3 is equal to 0 0 0. As such, no applied forces, at least visibly applied here. Whatever happens because of the boundary conditions, right? Some sort of push is given by this nut to the port and the tube, and the force gets applied as a result of that. That will be categorized as a bound as a reaction force, not the applied force. So, and we'll see that. Now this one is your system equation. Now if you add them together, you get 95,000 pi minus 50,000 pi. You're just simplifying the earlier step, nothing new here. 1,000 pi minus 50,000 pi 50,000 pi 0. minus 45,000 pi 0 and 45,000 u1 u2 u3, and you have 0 0 0. Again, let me put the this curly bracket at a distance, and now it should be very clear why I'm doing this. Now this time to apply the boundary conditions. Now you have to apply the boundary, and just recall what those boundary conditions are. Number one, u1 is equal to 0, and here I'm going to apply. I could apply it in many different ways. I could have just because it's 0, I'll just remove this, but I'm going to use the simple penalty method for this one and the MPC method for u2 and u3. So let's recall what boundary conditions are there for us. u1 is equal to 0 specified. As far as u2 and u3 are concerned, they are u2 minus u3 is equal to 0.4, and we have just seen that this is a multi-point constraint problem. So b2 is 1, b3 is equal to minus 1, and b naught is equal to 0.4. Therefore b2 is equal to beta 2 is equal to 1, beta 3 is equal to minus 1, and beta naught is equal to 0.4. Now recall from the development that we did when we were studying this multi-point constraint method, we have to apply this value, c beta 1 square here, but in this case instead of beta 1 we are going to use beta 2 and beta 3. So we are going to apply on the diagonal term, and for the third element, the u3, we have to apply on this diagonal term, but the thinking is the same. Just replace beta the u1 and u2 by u2 and u3. So for this we also need a number c, and what should that number be? Similarly, as we did in the simple penalty method, there is no need to change the number c here. C was, we had agreed upon a c, and that was the highest value in the K matrix multiplied by 10 raised to the power 6. The highest value turns out to be this. So C, we are going to use 95,000 pi into 10 raised to the power 6. This should be good enough for us. So what we do here is we have to apply certain quantities, and I'm going to apply that and then explain why I'm doing that. For this one, this is not the topic that we studied today. We already know what we do with this kind of a problem. What we do is we add plus c 95,000 pi into 10 raised to the power 6. That is all we do. This is simple penalty method. We just apply c here. So this is what we do. And on the right hand side, we simply apply 0 here. Why 0? I'm going to explain. What I have done here is applied c, and c is nothing but this, and here I was supposed to apply plus ca1 if there was a boundary condition or point, this degree of freedom 1, but since this a1 turns out to be 0, there is 0 boundary condition, so it becomes 0. So this is what we did last time. Now multi-point boundary conditions u2 and u, and this boundary condition is applied. This the first 0 boundary condition is applied. Now we deal with u2 and u3. Now this is more interesting, and this is what we did today. So what I do is, for this I add in this 95,000 pi into 10 raised to the power 6 into 1 square, and let me explain what this is. This is whatever the value is plus c beta 2 square. This is the solution that we reached today. We must apply this to apply this sort of boundary condition, but we also have to apply on this off diagonal term, and by off diagonal I mean this is 2 2, this is 3 3. These will be applied, but here in 2 3 and 3 2 place also we need to apply something. Just like here. On the diagonal terms we applied something, but off diagonal terms also we applied something. And the off diagonal term is nothing but again plus 95,000 pi into 10 raised to the power 6 into 1 into minus 1. Let me, and here on the right hand side, let me add here plus 95,000 pi into 1 into 0.4. And what is these terms? Let me explain. Here you add plus c beta square, beta 2 square, beta 2 we know is 1. And here after the term you have plus c into beta 1 into beta 2. And this right hand side you add the term c into beta 1 beta naught. We have these values here. Similarly for the third row, this is the diagonal term. So here again c to 10 raised to the power 6. Here also you need to multiply 10 raised to the power 6. Wherever you're going to use c 10 raised to 6, you have to add multiplied by minus 1 square. So what you're doing basically again here is this one plus c into beta 3 square, beta 3 being minus 1. And on the off diagonal term you add just like this 95,000 pi into 10 raised to the power 6 into, this time you have again minus 1 into 1, and this is plus beta 3 beta 2 c, or c beta 2 beta 3 to be more precise. And on the right hand side similarly plus 95,000 pi into 10 raised to the power 6 into, here you have minus 1 into 0.4, and that is plus c into beta 3 beta naught. These are the values that we are supposed to add whenever we want to apply the multi-point boundary condition. So the difference between these 2 and 3, these are multi-point constraints, you apply not only on the diagonal terms but also off diagonal terms, and there is some squares involved. Some on diagonal terms, square of the relevant beta. On the off diagonal term you have the product, and on the right hand side also there is a product between the beta naught and beta 2 in this case, beta naught and beta 3 in this case. The first one u1, that is simple boundary condition, so you just apply c here. There's no concept of beta 1 beta 2 or even beta naught here, obviously just one. And on the right hand side you are supposed to add c a1. A1 is the boundary condition that was to be applied. If it was a fixed boundary condition which is non-zero, then some number would have come here, but now it's a 0, so it remains 0. This is how you apply the boundary condition. Please make this correction. This is not beta 1 beta 2 plus, but beta 2 beta 3 here. Similarly, this is not beta 1 beta naught, but beta 2 beta naught. These values, beta 2 beta 3. Beta 1 is not even involved here in this problem. So now that we have applied the boundary conditions on this problem, now this matrix, this is still square, this is still symmetric, but now it is not singular, now it is convertible. So the next step is obviously the solution of this, and having taken utmost care not to drop any information by using pi's here, and avoiding decimal places. We now leave the rest to Excel to give us the exact values of U1, U2, U3, the accurate values, and they turn out to be 0.1894736 minus 0.2105263. These are from Excel. And if you take care of the accuracy, something similar you should get. Now, the next step after calculation of displacements is strains and then stresses. If we do the two steps in one go, this is how it would look like. For element 1, you have the Young's modulus 200 GPa converted to MPa here. Epsilon is this minus this over length 0.1894736 minus 0 over 100, which is 378.94 megapascals. This is the stress in the bolt, positive tensile, as expected. As for the brass tubing, you have this expression. Young modulus is half of that of steel, and the strain this minus this. Remember, this is the U1 with the first degree of freedom that is shared by the two. Minus 0.2105263 minus 0 over 100, which is minus 210.53 MPa. Tube. Now, your question actually ends here. But if we were to calculate the reaction forces as well, then we'll just use the equations that we have just derived today, and B2 U2. I'm tailoring them to this system. We derived for U1 and U2, but here this system is different, so I'm just adjusted for U2 and U3 boundary conditions. And this is again trying to preserve the accuracy and avoiding decimal numbers. 10 raised to power 6. This is C. This is your beta 2, and then you have again you have the values 0.1894736. I'm not writing 1 because it's just it doesn't change anything. And as for beta 3, this is minus 1 and minus, and you have this minus value for beta 3 and minus value for U3. So again it becomes plus. So I'm just writing it directly. 2105263 minus 0.4. This is the value of beta naught. And this is slightly less than 0.4. This comes negative, negative, and negative, positive. So you get 29845.1 newtons. This is the reaction force R2. For R3, beta 3, the rest is the same. Beta 2 U2 plus beta 3 U3 minus beta naught. And this is the same. Here you have minus 1 now. Beta 3 is minus 1. In this, you have the same value as this because these are the same. And because in this case there's an extra minus 1 here, so R3 will be the same number but with a negative sign. Now if you were to divide these by areas, these are the reaction forces. So if you were to divide these by areas, you should get stress values. R2 and R3 are these forces applied on 2 and 3. Actually what you did was you gave displacement to this in this direction, stress state, displacement to this in that direction. The forces are caused by as a result of these displacements. So these are reaction forces. So these reaction forces, if you divide by the respective areas, you should get something similar to these values. But obviously we don't calculate stresses like that. Our route is this one. So this is just for as a means of checking your expression, these expressions. And in reality you'll rarely use these values, these formulas. But now let's see what this means. This means that this was your these are the two elements. For the node 1 is common, node 2, node 3, this is bolt, this is tube. On the board there is a force of 29,845.1 Newton, reaction force, as a result of the displacement given by the nut. And on the tube there is an equal force of 29,845.1 Newton in compression. So what happens is, what about node 1? What is happening here? If you use your reaction formula for node 1, that was not multi-point constraint, it was simple constraint used by penalty. So that was minus C U1 minus A1, which is, in this case U1 we sought to apply, A1 is what we wanted to apply, and U1 that was 0. We wanted to apply 0 boundary condition, and what got applied was also 0. So you have 0 minus 0, that is 0. There is no boundary, there is no reaction force here. In reality what is happening is there is a 29,845.1 tensile force here, so there must be a force here also, because this is in tension. Force always occurs in pairs. As far as this is concerned, this is compression, so again there should be an equal and opposite compression. So actually there are forces here, that's why this is in tension, this is in compression. But what happens is, because these are equal and opposite, they again get cancelled. So on node 1, because it is shared by both, actually there is no force, because these cancel each other out. So this is as far as the reaction forces are concerned. Now that's the end of this question. And you would have noticed that I have used very elaborate expressions for these. I could have taken 0.189 or something like that, but I made it a point to use up to 6 or 7 decimal places. Now if you don't do this kind of thing here, because remember that we were very particular about retaining our accuracy in all the calculations that we did on paper, and this is the result that you got as a result. Now if you use a curtailed value here, there will be some problems, more so in the calculation of reaction forces. Somewhat they will also be reflected in the calculation of stresses and strains, but for stresses and strains, even if a curtailed figure is used, you'll get reasonably good results. But when you use curtailed values for calculation of reaction forces, then recall that very big numbers are involved here. So even a slight inaccuracy here will cause the reaction forces to be very much away from the real forces. So you should be very careful about using exact figures here. Again, this is of limited value as far as practice is concerned, but it's good practice, as mentioned earlier, to use double precision arithmetic and to retain as much information as you can to get best results. Thank you.